joint work with 고성진, 세훈강, 임혁도, 정은피, Professor 혁중권, and Dr. Adel Sobi. Professor Kwon and Dr. Sobi are our main advisors for this work. I'm very honored to be invited here. We are going to talk about the hidden problem over band functions. We studied its quantum solutions and implemented it in a real quantum device. In this talk, we show the performance and limitations of quantum computers in the RISC era. Let's start with our motivation. We were motivated from finding quantum advantages, and the leadership problem for band functions is one of the problems that we can find quantum advantages. The reason is that when it comes to band functions, the leadership problem can be reduced to abelian hidden subgroup problem, so we can find quantum advantages. One of the applications of leadership problem is related to Poly 105. Poly 105 is a massive authentication code. It is widely used when sending messages. Boneteng and Nayakwa paper, they built quantum attack on Poly 105 based on leadership problem. Let me introduce the leadership problem. Let f and g are band functions defined on d2 to dn. And a band function is a special type of Boolean function. When even f and g satisfy this equation for all f in g, what we have to do is to retrieve x, the leadership. Also, we assume that there exist oracles that compute f and g. Let me ask that how many times do we query the oracles? The answers in this table. As you can see, the quantum algorithms are exponentially faster than classical ones. There are two quantum solutions we introduced. The one is called Rattler's algorithm. In this case, f tilde is given. F tilde is the Fourier transform function of f. The other is called Rattler-Gavinsky algorithm. In this case, f tilde is not accessible. So the latter case is more general. In the Rattler's algorithm, the key idea is that for Boolean functions, the quantum Fourier transform is equivalent to the Hadamard transform. So we can calculate the Fourier transform easily by applying Hadamard gates only, like this. Here's our result. In this example, we said the leadership S is 1/1. In the simulation results, we can get the solution with 100% probability. On the other hand, in a real device, we can get the solution with about 60% probability. Anyway, this noise level, it seems that this noise level is negligible. And this is Rattler-Gavinsky algorithm. As I mentioned before, in this case, we cannot access to the Fourier transform function f. Here is the circuit. After the measurement, we get b comma y string, and this is not the initial set. In the previous algorithm, we get S state after measurement. Instead, in this case, the bit string b comma y is orthogonal to 1 comma s. However, this means that b comma y string is orthogonal to 1 comma s, and I saying the word orthogonal, not in the usual sense. We define the orthogonality by this dot product, and this dot product is defined by this modular 2 addition. In this example, to retrieve S, we choose 4 different states from this outcome, and put together them into a system of linear equations like this. And by solving these equations, finally we get X like this. In this table, we can check that S comma 1, the dot product of S comma 1 and Y comma B is always equal to 0. These are calculation results. Here are our implementation results. In the real device, there are too many states compared to simulation results. We expected only 16 states like simulation results, but there are too many. So we have to distill out some wrong states. But it is hard to do because the probabilities are not dramatically different each other. So we conclude that in a real device, this algorithm does not perform well, we think. And although this algorithm is fragile to noise, we guess that much of the errors came from Toffoli gates. Toffoli gates are made of the oracles. In the oracle, there are 2 Toffoli gates and 1 SeKang gate, and we need more swap gates to implement it. And as you know, they are likely to cause noises. Then we summarize our results. We implemented 2 algorithms, and we show that Rattler's algorithm performs well. However, the Rattler-Evans algorithm does not provide meaningful results because of noise. And the error origins from the Toffoli gate we get, which need heavy resources. So we recommend as future work. It is good to do noise analysis on Toffoli gate, will be good. And this is our GitHub repo. If you are interested in, please check this out. Thank you.
감사합니다.